This talk is brought to you by the Bamberg Mathematical Consciousness Science Initiative.
Thank you so much, Johannes, and thank you, Lara, and everyone for organizing. Yeah, so I think it's a great opportunity. It comes at the right time for me to brainstorm a little bit with everybody about these ideas that we're developing and the data that's starting to come in. And I say straight up that I'm not a mathematician, but it feels like the work is pulling me in a mathematical direction. So I'm very much looking forward to hearing your thoughts on what's happening here. So yeah, so this is work in progress, and I'm presenting it here in the spirit of collaboration and discussion, and I welcome your critical feedback. So by way of introduction, to say a little bit more than what I put there in the form, so I'm the head of the Embodied Cognitive Science Unit at OIST, and our scientific mission is to study the human mind, and to do it from an embodied cognition point of view. That means that although we focus also on the brain, we have a EEG lab. We also record all the other physiology that we can grab from the body, and we also record all the sensory motor information and things like that. And I show some examples. But what differentiates us from, let's say, an animal behavior or animal neuroscience lab is that we also need to consider what's going on in our environment, which is very different from usual animal sensory motor loops because we're embedded in social environments, cultural environments, and technological environments. And so we're really dealing with one of the most complex phenomena that we can study, where we have everything from sociology, to psychology and consciousness science, going all the way down to, I don't know, thermodynamics and physics of living bodies, right? So somehow we have to manage to condense all of that into something that is tractable, which is not easy. But I'll show you some examples of how we try to manage that complexity. So one of the aims of this workshop is also to take a look at the historical roots of paradigms. So let me just give a few slides to kind of situate us in this broader context. Some of the deep inspirations for our work comes from the 90s, where embodied cognition first emerged, especially with this book, The Embodied Mind by Varela and colleagues. And they drew on an older tradition in sensory substitution research, in developmental psychology, robotics, where people realized how important action is. So it was basically putting embodied action to the forefront, and saying it's the foundations for perceptions, it's the foundation for cognition. Some of the work that they were citing was already quite old at the time. So this book came out in 1991, but some of the examples that they drew on came from the 60s, so that was already a bit old. And so one of the issues here is that why didn't we have more recent examples to draw on? And also, this book came out in 91, right now we're in 2025. If we had to say what are the most important experimental proofs or demonstrations for the embodied approach, what are they? And if we would still have to say, well, Bach-y-Rita 1969 and Held in 1963, then that shows that something is not quite right with our paradigm, right? So one of the things that we really want to do is say, what would those new paradigms look like, experimental paradigms, to put this on a proper foundation? Um, I should also say that consciousness comes in also into this book, was one of the big topics, and they try to dissolve, as they say, the hard problem of consciousness by building dynamical systems bridges with neural dynamics, in particular phase synchrony. And then the idea was that perceiving is a form of action in the world. This is Noe's a very popular book. And we were very interested in this idea and putting this to a modern test. But then we had the problem. How do we define an action? What really is an action compared to just mere movement? And the early work in the embodied cognition approach didn't have a way of operationalizing this properly. But then with Di Paolo at the University of Sussex and his group, some ideas started to be formalized in which value was associated with a particular kind of embodiment, organismic embodiment, which is precariousness, which where things are at stake for the organism because it is self-producing. And then on this basis, then you can define an action essentially as a particular kind of sensory motor loop, which is being regulated by the organism to achieve some kind of goal. And I have this at the top right. The rest of the slide is from a different presentation, but I leave it here just maybe we can go back to the discussion. I think there's some interesting developments here too, where our ideas of the necessity of organismic autopoietic embodiment and adaptivity as the basis for sense making is starting to be challenged by advances in AI in ways that we didn't foresee, 10, 15 years ago. So there's something happening here which requires some deeper thinking too. So anyway, so going back to this action and perception, this embodied action approach. So the way in which we try to put it on the more modern experimental foundation is to develop a simple sensor substitution device, which we call the inactive torch, which is basically just a haptic vibration module attached to an infrared sensor that can measure distances. But by keeping it simple, what we can do is ask people to learn again to how to perceive their environment, which is very useful because most of the modalities we're so used to it, it's very hard to see the process of acquisition of this kind of skill. So we asked them to learn something which they hadn't done before, which is how can you use touch to perceive at a distance effectively? And then what we can do is record that process and then play it back, play the movements and the sensations back to another participant and ask them to do the same kind of perceptual task. And if action and active regulation and all of that is essential for perceptual experience, then the prediction should be that the passive condition ones should have a much harder time to achieve these tasks. Unfortunately, in all of our work, we never found a strong difference. So there's this paper from back in 2012 where we didn't find a very strong evidence that there was differences. We tried it again with a different setup, a bit more controlled. And the middle paper here, again, we didn't find any difference. So we already put the title, Where's the Action and Perception? We still thought maybe we did something wrong. So maybe we need to get a lot more free movement or something like that. So we created this really sophisticated setup that you see at the bottom right here, where people were allowed to freely move their arm and generate a sensory motor loop of their own. And then we would have the robot play back the movement to the passive condition. And again, we didn't find any significant difference between the active and passive conditions. In fact, sometimes the passive people seem to be better, have more accuracy in terms of perceptual discrimination tasks they had to solve, as if the active condition somehow was interfering with the perception. And that then, really made me think we need to rethink this. We've been banging our head against this for like a decade or so. Negative result after negative result, and we were not the only ones suffering, getting this program started. So it felt like we need to rethink what we mean by agency and what role it plays in perception. So that brought me to reconceptualize things in terms of eruption theory. So now this was the his kind of historical part. So now let me get into the kind of current work that we're doing. It was basically an attempt to revisit the foundational premises of the inactive approach and try to derive from kind of first principle way some of the expectations of how action and perception should be related to each other. So basically, it's a way of putting our cards on the table, right? So axiom one is motivational efficacy. An agent's motivations as such make a difference to the material basis of the agent's behavior or the physiological basis of the agent's behavior. And this is key. So this is the kind of realism about agency as a starting point, right? Agency does make a difference. Your norms make a difference. Your goals make a difference. Your beliefs make a difference. And if you don't buy this axiom, basically our conversation already stops here, right? Then we're in different worlds. Surprisingly, many people don't subscribe to this axiom, but it's kind of helpful to put it out there as the first one, because then you can kind of like focus in on those theories or those research programs which actually, are relevant for this. But being in an experimental lab, and especially being in a natural sciences university, the axiom two comes, quickly on the heels, which is to say that we can't directly measure agency or activity or action or intentions. When we go in and do our EEG recordings or physiology recordings, we can measure voltage, conductance, we can measure displacement, we can measure, heat emission or something. depends on what you're looking for, but you will never measure directly that someone is intending to do something, for example. So in that sense, if we agree on axiom one, then we must take axiom two seriously, which is that we have an incomplete picture of what reality amounts to. What we measure is the observables we can measure are not giving us the full ontology, and there's something else that could be making a difference too, even if we don't directly observe it. And this is the kind of classical mind-body problem in a way, recovered again. But I think that the one advantage here is that this is a totally an operationalizable version of it, in the sense that the axiom one and two don't negate each other as long as we don't make the additional assumption that axiom two gives us the full picture. So as long as we don't say that all the observables that we can get is all there is. And so axiom three basically just makes that explicit and says, actually, even already at the level of the physics of the situation, the current behavior of the system is undetermined by its material basis or by its past, which means that intrinsically there's an uncertainty factor at play. And the idea is that this uncertainty factor then gives us some room with which we can play in order to fit in axiom one, basically. So let me first do this for the intentional direction. I know this is a workshop on consciousness, so I'll try to focus more on consciousness in a bit, but actually the principles are a little bit easier to explain from this point of view. So from the mind to the behavior. We have this chapter coming out where we propose what we call the participation criterion. Essentially, end-directedness of a behavior entails that in principle, it's distinguishable in measurement from one without end-directedness. And this comes actually from some analysis that we did of Schrödinger's work on the mind-body problem. And he has this nice way of going back to the ancient Greeks and deriving the mind-body problem from their principles of the nature of the scientific world image. And essentially, he kind of is really puzzled, and he has really like evocative ways of phrasing this problem. But basically, he says that we can't find ourselves inside the scientific world image. And essentially we can make no difference. Okay, so he calls it the exclusion principle. We're excluded in our actions and intentions from the scientific world image. I think that's unacceptable, right? That it would violate axiom number one, which says that we do make a difference somehow. And so the left-hand side is the alternative picture, that we have to have some way of finding a difference in the scientific world picture that corresponds to the end-directedness of our mental states. Okay. But it's not a saying that, we can directly find it there. So it's not a representationalism. It's not like there's a homunculus inside our head that we can measure. So in a sense, what we're looking for is indirect signatures of something that's not directly observable, using the usual instruments. That's why I say here it's an unintelligible measurable difference. Unintelligible in the sense that it cannot be reduced to causal factors of observables that we can measure. Okay, so and if a theory doesn't have this postulate, it doesn't satisfy the participation criterion, again, the idea is that to some extent we can ignore it and move on, right? So it's from the 100 or so theories of agency and consciousness, if they don't satisfy this principle, not even in principle, then maybe we can move on and look for different theories. So how does this relate to consciousness? Kim's book, Physicalism or something near enough, gives a nice clear overview of these problems. And his idea is that, we should buy into reductionism, and that's how we can get causality for agency and so on. But at the end of the book, he admits that there's one issue that he can't solve that way, and that's because the hard problem of consciousness remains unsolved. And basically, the point is that sometimes we can act because of our experiences, right? And so the problem is that if we don't have a scientific account for experiences, conscious experiences, and to the extent that those can make a difference to how we behave, then everything is up in the air again. We can't explain human behavior, essentially. So these things are interlocking problems. It's not that we can take them in isolation. And so how does consciousness make a difference? And here's one of Johannes's paper, which I very much liked because it's one of the few that makes this issue explicit in a way similar to what we call the participation criterion. He says consciousness is dynamically relevant, simply put, if, according to a theory of consciousness, it is relevant for the temporal evolution of a system states. It's a nice physics style way of putting the participation criterion, and I think this is exactly the kind of criterion that we need, right? So if let me just go, if we don't have an even in principle possibility of satisfying this dynamical relevance, I think this theory can be ignored, basically. Again, it's a nice sorting method, right? We can just, in that case, move on and consider a different kind of theory. Now, going back to the inactive approach, the embodied approach, does it satisfy the participation criterion? Does it satisfy dynamical relevance? At least it says it can. And when I was a bit younger, one of the reasons why I was interested in this approach is precisely because it makes the claim that it solves the hard problem of consciousness and in a way in which allows it to be causally efficacious. And I'm not going to go through all the text here because we still have a few slides to go. But there's this paper that we recently published on the right-hand side where we in detail go through the literature of neurophenomenology and try to work out how did they think that they were going to explain how consciousness as such could make a difference to neural dynamics and to behavior. And basically, what we argue is that, the ambition was there, it was on the right track, but ultimately it falls short of giving us an account of how consciousness could be dynamically relevant in the way that Johannes puts it in his paper. All right. So that leads me to give a kind of complementary participation criterion for consciousness now, which is the other direction of the mind-body problem, right? Now going from the brain-body up to consciousness in a way. A scientific theory of consciousness must be able to explain how the presence of consciousness makes a difference to the brain and body compared to its absence. Now, this is really interesting because mm, I think most people would agree that, okay, if we want to solve the problem of mental causation, then we have to have some way in which there's a difference in the brain-body system such that behavior gets changed, right? But it seems kind of natural still to say that the other direction of this relationship, going from the brain and the body to the consciousness, doesn't necessarily have to make any difference to the brain or or to the body. In fact, most theories don't assume this, right? They would say, for example, that conscious perception supervenes on, I don't know, activity in the visual cortex or something like that, right? So, or is identical with activity in the visual cortex. In that case, you can have philosophical zombies, right? So another way of putting this is to say philosophical zombie is precisely defined against participation criterion. It basically means that I could have a total account of the physical world, the natural world, and I wouldn't be able to tell whether consciousness was present or not. Whereas this principle says exactly the opposite, right? So it means that there must be a measurable, in principle, measurable difference if consciousness is present compared to absent. Okay. But what could that difference be? That's really tough to think about. But in this book by Sarah Walker, she has a very interesting criterion, which is basically relating to counterfactualities. And I think that's kind of pointing in the right direction. So she says, consciousness creates the possibility for things to exist that otherwise couldn't because they did not exist in the past. It is what allows the counterfactual, what could have been or could be, to become the actual. And what they have in mind, what she has in mind in this book, is large-scale objects, like the Taj Mahal, right? So the fact that we have a Taj Mahal in the universe can be basically thought of as evidence that consciousness is present. And that's kind of a cool argument. And I recommend that you take a closer look at the book. But it's kind of like large scale, right? So we basically would need to find a way of translating this idea into something that is, relevant to the scale of our bodies. And so here's the picture that I would propose. We've already talked a little bit about mental causation on the left-hand side. Okay, so we've got unobservable mental states, whether they are conscious experience or intentions or goals or whatever, beliefs, desires, and so on. Doesn't really matter. At this point, we're talking in very general terms. And these states we can't directly observe using our scientific instruments. Yet we're realist about them and that they make a difference. Therefore, at the level of what we can measure, which is the material basis of our behavior, the difference is made by these unobservables cannot be reduced to any kind of causal factors at that level of observation. And so that means to the extent that there are differences being made by those unobservables, they are unintelligible. And that particular unintelligibility I call eruption. Basically, there's an additional noise factor or uncertainty factor which erupts into what we're measuring over there, and which cannot be explained away, not even in principle. And I will show some examples of that in a moment. The other side of this is going in the other direction. So let's say we're tracing a stimulus from something being presented to the subject to their through their perceptual organs into their brain, and at some point the person says, "Oh yeah, now I experience the stimulus." Well, from the point of view of what we can measure, at some point we lose track of this chain of cause and effect because the final effect that there was a conscious experience we can't measure. And so there's a kind of like a cause without an effect, which we then propose to call absorption in the sense that there's a reduction, a counterfactual reduction in the kind of variability that we would have expected downstream. There's a reduction in variability, a spontaneous reduction. Okay, so we've got these two operators. Um, Let me just skip that. I already said that. Let me give you a couple of brief examples to motivate them and to relate them to existing literature. Here's a classic work by Varela's group, which kind of initiated some of the neurophenomenology research program, where they asked people to see these faces, a meaningful face and an inverted face, and people had to decide whether they could see the face or not. And then we have this phase synchrony diagram over time from zero after stimulus presentation. And then the big news that made it into Nature at the time was that there's this peak around 200, 300 milliseconds after stimulus presentation, which for the case of meaningful faces is a significant increase in large-scale neural phase synchrony. Okay, and they associated this phase synchrony with the emergence of a conscious person. And that's interesting, right? Phase synchrony means there's a reduction in the kind of variability that the system has. And yet, we also have here, which is something that didn't quite talk about so much at the time, it's a moment of phase scattering. It's actually even stronger effect, where we have more than baseline variability. And so, just one way of thinking about this is that this is a moment of absorption, and this is the moment of eruption, which basically then, has to do with the action of responding to the stimulus. But the nice thing is that, this is empirically driven, and now we can actually do this from first principles in a way. Yeah, so then the other way around, so this non-word variability, just give another example in the neuroscience of free will literature. There's been growing interest in stochastic accumulator models to explain what's going on. I don't have time to go through all of this, but let me just read the conclusion here by Sugar et al. In this recent paper, where they say theorists who want to identify the source of the action as the agent will have to tell a story that somehow makes a case for the noisy trigger being part of or attributable to the agent. And so I propose that eruption is exactly that. And it's nice again that we came at this from a first principles point of view, and they came at this from a kind of empirical, statistical point of view, but we're actually converging on the same insight. So that's nice. All right, so now we have these two operators. Let me just show you one example of how it allows us to do work in the science of consciousness. This kind of study, got a lot of attention when it came out, which is basically applying complexity measures of different sort, entropy measures of different sorts to altered states of consciousness. And there was a lot of work already showing that if you give people not depressants, anesthetic agents, so they're falling unconscious, complexity goes down compared to baseline, and also in deep dreamy sleep you find that. But if you give them psychedelics, complexity goes up. And so there was some kind of interpretation saying that maybe this is evidence that these kind of drugs give you a higher than normal level of consciousness because complexity is higher than baseline. Um, but one of the issues here is that they do not separate between agency and consciousness or agency and subjectivity properly, right? You could also argue that if you're unconscious, you can't do anything. So there's no eruptions, there's no agency, right? And whereas if you're under a psychedelic drug, well, actually, you're probably having a pretty high cognitive load just to keep stability and, preventing your ego from dissolving and I don't know what. So, both are kind of co-correlating in these different ways. So, what's is actually being measured here? So they interpret it in terms of levels of awareness, but from the point of view of eruption theory, actually, maybe what they're measuring is agency because there's an increased spontaneous diversity in the signal, and that's more the signature of eruption than absorption. So then Pedro Mediano pointed this nice paper out to me, which actually validates this intuition, which is very nice. So what they did, they had a paradigm where people were falling unconscious with anesthesia, and their expectation was that neural complexity would go down, and it does. But in this case, they had a nice trick, which is that while people were falling unconscious, they had to perform this task, some kind of like computer-based task. And then they found that for some people, their complexity was actually higher than baseline while they were falling unconscious. And it would turn out that it was the people who managed to continue having a high performance at the task. And so we have a nice association here in the sense that both of these people are falling unconscious because they're being administered an anesthetic. And yet, for the people who are struggling with a lot of cognitive effort to maintain their performance, we find that they have higher complexity and higher entropy than baseline. So it suggests that what we're measuring here indeed has more to do with the side of eruption than with absorption. So that's nice that we can actually dissociate these two signals. So this is then the overall picture that I brought out last year, which is basically saying that we need to take seriously that there are some boundaries in nature, in the real world, that can't be easily crossed. And I just call this here a black box middle. So it means that when we are measuring things in the body, there will be things happening that have their reason for happening that in things that we cannot directly observe, and vice versa. We can also have things happening in the body that have an effect somewhere where we can't observe it. And we basically just need to work with the uncertainty that comes from this black box boundary. And in a more recent little comment with Morris Creek later, we kind of refined this a little bit to say that this gives us actually a way of defining operationally what we mean by the embodied mind. It's basically that part of embodiment which is being affected by eruption and absorption. There's also the other side of the story from the point of view of the subject, from the first person point of view. There's also a black box boundary, and this has already been a long topic in phenomenology in terms of the alterity that is intrinsic to consciousness. So we're not fully self-transparent, and there's lots of interesting work on that side of the interface, but that will be another talk, so I'll leave that part for now. All right, so the mathematics. What does this boundary then mean for mathematics? So a really big moment for me came when I attended a lecture on dimensional analysis in physics, and I was like, oh my goodness, why did we never do this in science of consciousness? The basic thing is that in physics, you can get a lot of work done by just thinking about the units of what you're trying to relate. And you have to be careful that the units match. And if they don't match, you know that there's something wrong with what you're doing, right? So when we work across the mind-body interface, we face a similar issue in the sense that, let's say, what Vareda tried to do was relate meaning and experience, a meaningful stimulus, with activity in the brain. And he was measuring EEG. So in this case, we're measuring changes in voltage or something like that, microvolts. Well, the problem is that meaning doesn't come in units of microvolts. So then, if we have a transactional process and we want to relate the two things together, well, we already know that it can't be expressed in terms of unit volts. So then how do we do this? Well, it looks like, well, then we have a problem because how do we ever relate something with the physical world? But it turns out there are many aspects of the physical world that are not expressed in physical standard units. So there are dimensionless constants, for example, and there could be ratios and things like that. And so maybe it's not for nothing that he used relative phase as the way of capturing things, because precisely relative phase is a unitless measure. It's a reorientation, it's a geometric reorientation in some kind of state space, but it doesn't have a physical constant associated with it, a physical unit, I mean. And so, and the other thing is that and we probably want to look for things that are multiplicative, because in a way, even if there was a unit on the side of consciousness and we don't know what it doesn't matter as long as the operation is multiplicative, because then the units don't matter, because then you can bring things together. Like, you can have kilometers per hour, and when you're driving, these are two different units, but they're combined together because it's a kind of multiplicative operation. You couldn't add a kilometer to an hour. I cannot say 1 kilometer plus 1 hour. That doesn't work. But yeah, if I can say 1 kilometer per hour, like divided by, that's fine. There's no problem there. So basically, we're looking for multiplicative operations. And probably we also need some kind of principle of balance or symmetry, in the sense that we have to be a little bit careful in terms of energy conservation and things like that. That's a really subtle point, and it's quite difficult to think through that carefully, because we still don't know so much about these kind of open thermodynamic systems that living bodies are, to really understand the thermodynamics of it. But anyway, there's some issues there that we need to take care of too. And I'm just putting Euler's E here because it's one of those constants where the rate of change is equal to itself as a quantity. So it might be an interesting conversion unit, actually. Okay, so then that's the kind of interface, but then the body, what does the body bring to this? Because, it's one thing to say that, maybe eruptions happen, but then the body still has to do useful work with that. And it has to somehow be sensitive to this. First of all, how does it know which of the many fluctuations that are going on are actually eruptions rather than just pure background noise? And then it has to somehow respond to that and take appropriate action, right? So, that's a difficult challenge, but there are some interesting principles that we can work with. So first of all, we're looking for stochastic fluctuations that go beyond baseline. That's a kind of signature of eruption. And in terms of absorption, what we're looking for could be something like a broken discrete symmetry. So what I'd like as a kind of example of this is homochirality in chemistry at the origin of life. So you can have molecules that are identical, except for that they have their thumbs sticking out in opposite directions, basically. And that means that, they're not mirror images. You can't put them on top of each other. There's an anti-symmetry involved. But it also means that if you only have one hand and you don't see the other hand, it's absent. It's a counterfactual absence, because you know that this molecule could have also been expressed in this way, but you don't see it present. And that's an interesting signature for absorption. It's an internal relationship to a counterfactual possibility that was not realized. So kind of like spontaneous absence of variability. Another thing to say is that these two signatures, stochasticity and this kind of like spontaneous reduction of variability, are not compatible with each other. One is essentially injecting noise, and the other one is saying, I need, reduced variability. So that means that they must happen in different parts, or they must happen at different time, maybe in rhythmic alteration or at different scales. And if they happen together, there will probably be some interference. And this gives one way of linking back to our agency work, where we're basically forcing people to perceive and act at the same time. This inactive torch was, vibrating while people were moving around, and the active people had to both agentially control their movement and at the same time try to perform a perceptual task using the same hand with the same action, right? So according to this theory, that would make it difficult for them. And if you were just passively being moved through that sensorimeter loop, maybe it would have been easier for you to do the task. So that's already an interesting loop back to the original empirical data. So we can do a kind of very simple mathematical model. Again, like I said, I'm not a mathematician, so this is, me just dipping my fingers into something that, I'm very excited to get more into, but I'm looking forward to hearing your feedback. So a very simple way of modeling eruptions then would be as a kind of Poisson process, that we have stochastic events happening once in a while, which are these eruptions, and then we can basically talk about the rate of this process. And interestingly, if we set the rate to E, then we get these nice curves. Basically, now using the total time horizon as one, we get a curve that says the likelihood of having had no event so far, the P0 curve, and the likelihood of having had one event so far, which is this other curve. And they meet at this point, which is basically 1 divided by E. And again, 1 divided by E in terms of probability, which is the point at which you're more likely to have had at least one event compared to non-event. So it's a very important threshold for looking for eruption events. And the other reason why this is a good way of looking at things is because this 1 divided by E turns out to be related to decision theory. It's a very famous result coming from the 50s and 60s from the last century, which is sometimes known as the secretary problem or the 37% rule. And let me just illustrate it like this. So imagine that you have to hire someone into your group, and they're coming at a random order into your office, and each time you have to decide yes or no. And if you say no, that's it, you can't go back. But if you say yes, you don't know what other candidates might be walking through your door. So how do you know what to do? You don't want to hire the first person walking through your door because there could be better ones. But if you wait until the last candidate, maybe the best one, was already there, and you didn't say yes at the right time. So it's a kind of constraint problem. And it turns out mathematically that what you should do is weight 1 divided by E of the total number of candidates to build up a reference frame, and then afterwards switch modes and then commit to the next best candidate that comes through your door. Okay, and this 1 divided by E can be generalized to a time sequence as well, which is then called the 1 divided by E law. All right, so we can model this also simply. It looks like this. Here are the constraints. We can basically show that these different ratios of waiting times, how long you should wait. This is the optimum here, which is the 1 divided by E. And then you should basically not do anything until that time. And then we can plot how likely you are to make the decision afterwards. And there's some simple equations to put to that. All right, so far the math should be relatively straightforward. And what I will show now is that with this framework, the theory and then the kind of model expression of it, we can make sense of our data in a way that we haven't been able to do for years. So this is really why it's exciting to me that we've been banging our head against how to analyze our data, and suddenly things seem to be falling into place. So this is the perceptual crossing experiment. I'm not going to explain it in too much detail. It's not so important right now, but basically people have the task of deciding whether the haptic information that they receive in their hand at any point in time comes from another person's avatar or from some other object. So the question is it socially mediated touch, or is it just a normal haptic feedback? So it's kind of perceptual discrimination task, okay? And we've got all this data online, and the interface is also available online and everything. So it's basically if you want to play with this data, it's already there for you to play with. This is the kind of data that comes out of it. It's a bunch of time series, but it's nice because we've got the full sensory motor loop. We've got here the position in space. We know what's happening in their environment. This is the speed, so that like how much movement they're making. This is the activation of the vibration in their hand, so we got that side too. So gives us the full sensor motor loop over time, and then this gives us an insight in what's happening in their minds. Basically, this person saying here, they're giving us a click saying, I think I'm interacting with the other person. I feel I'm interacting, and we can go back and say, yep, they were actually on top of the other person at that time. And then this other player is giving us this signal later on. But by that time, the red player had moved away, and so this actually is a mistake. He's identifying the static object that's not moving as haptic, socially mediated touch, when it's actually not. And then we have all the physiology that goes with it, and so we can correlate it. And for example, interestingly, in this case, we've got some kind of entrainment where the breathing of one person it goes through 2 cycles with respect to 1 cycle of the other person. So there's a kind of 2-to-1 entrainment here. All right, so it turns out that this works. So if we plot the probability density of them giving us these click signals over a trial time, it turns out that the peak is just after optimal waiting time. So we've got a slightly asymmetrically skewed distribution, which peaks just after the optimal waiting time. That's interesting. So when we saw that, we got quite excited. Now let's try to explore the physiology of what underneath this. And this is for over 1,000 clicks. So this is quite a good set of data. First question, what's the evidence? So who are the candidates, so to speak, that move through the person's mind that they're responding to? So we can look at the haptic feedback distribution over total time horizon, and it ramps up very quickly and stays pretty much steady. And when I saw it, it was very surprising because I can just plot this pink line with this equation here, this exponential. But it turns out that the 2 constants of this exponential encodes the optimal waiting time and the remainder of the trial. Now, again, if someone with more mathematical skills than me can explain this to me why it happened like this, I'd be very grateful. So we basically got 1 divided by e here, and then minus 1, 1 minus 1 divided by e, which is the rest of this trial in the asymptote. And what that means is that by the 1 over divided by e time, they will have seen 1 divided by e of the total possible stimulations in the experiment. And again, this is over 1,000 trials. So somehow the people self-organize the amount of sensory stimulation that they receive to be the optimal fraction of what they should have seen before committing to a decision. That's quite interesting. I don't know, how do they do that? It's a good question. And also, we can look at the movement side, and here we've got E divided by 10 as the kind of average likelihood of being in motion. And there's also, if you're looking at the frequency spectrum, there's a kind of slight oscillation here in the 10-second spectrum. And so it shows us that the 10-second rhythm also is important with respect to action, and we'll get back to that. Now, what's happening in the brain? Now, there's so many ways of trying to analyze the EEG that's coming out of the experiment. We have 64 channels. We can do all kinds of analysis. But what turned out to be very effective is to just take the global scalp potential, so averaging across all electrodes, across all trials, across all participants. We get over 1,000 trials here. And then what I said to do here to the script is say, give me a normalized version of this average signal where the first value is 0 and the largest value is equal to 1 divided by e. What would that look like? And this was what comes out. We've got this large 20-second fluctuation, which then switches at the optimal waiting time to become a 10-second rhythm, slightly decreasing. And overall, the trend is the P1, the probability of having one event occurring. Now, that's pretty cool. I don't know, nobody has looked at it this way before. Global scalp potential in this kind of task follows the Poisson process of a P1 curve. And on top of that, we've got these two rhythms sitting, the 20-second rhythm and the 10-second rhythm. All right, where does this come from? Interestingly, breathing, we can do the same thing. Lots of fluctuations, but the general tension of your lung, in this case, people having compressed their lung and then they relax and inhale more again, again, follows the same distribution. So I was getting a little bit worried that maybe we're just picking up the tension of the body, but it turns out that arousal actually gives us a different curve. So measuring skin conductance here, if I normalize it, it turns out to be the P0 curve, which is nice because it basically gives the body the time constant at which all the processes must run. Okay, so if I set myself poised at a particular kind of arousal level at the start of the trial, and I know what kind of level I need to be at the end, then I can fine tune the rate of decay, and that rate will basically be the rate which I can use to organize all the rest of the temporal characteristics of the decision-making process. Now, tiny little model, and I'm sure it can be done much better, but what we see in the global scalp potential is this interesting phase transition from a 20-second rhythm to a 10-second rhythm. So we've got a frequency doubling bifurcation. We can write it like this. We've got the minus sign, 2 pi up here, and if we multiply it by itself, so it's a squaring function, we get this here, which is basically a cosine with double the frequency. So we've got a kind of 90-degree shift and a faster frequency. Now that's interesting because we do have this 10-second signature associated with action, right? Now, what does that mean in terms of conscious experience? Well, we have that data too, fortunately, because we can ask people for every click that they made, how clear was the experience of the other person at that time? And interestingly, we have a decreasing trend here, which was at first surprising. We thought it would be the other way around, that people have better experiences if they interact for longer, right? That kind of makes intuitive sense, but it seems to be the opposite. What's going on here? So we looked at this a little bit more carefully, and it turns out that actually it's not that the clarity of the experience goes down per se, because the highest rated experiences, this pass rating 4, which is clear experience with the other person, if we ask before and after this optimal waiting time, there's almost no difference in the rate, the frequency of people responding with this clear awareness. It's almost the same. what happens is that after the optimal waiting time, we have twice as likely people responding in the I didn't experience anything, like no experience, or very unclear experience. So that's strange. So we've got an increase in the rate of responses, but they're all at the unclear level. Okay. But that's kind of interesting because going back to this, we have a doubling of frequency here after the optimal waiting time. And we have a doubling of the reporting of unclear experiences after waiting time. And that kind of makes sense, right? Because action is supposed to interfere with conscious experience. That's part of like the framework that we're developing. And we can look at this a little bit more closely. We can say if we divide the time series of clicks, whether they have no or vague experience or almost clear awareness, the likelihood of them clicking is has an oscillation only for the unclear experiences. And now I'm just very crudely superimposing the global scale potential on top of this. And you can see that in the up movement here is when we have an increased rate of responses, but they're basically unclear responses. So something about the intensity of change makes people more likely to click, but they're doing it in such a way that it interferes with the clarity of their experience. All right, so let me wrap up. Take home message of all of this so far. Theories of consciousness must satisfy the participation criterion. I think that's the number one. I think eruption theory is just one way of going about it, but essentially, should be our starting point. I think if we don't even have the ambition to satisfy this, to argue that consciousness must be dynamically relevant, as Johannes says, then we're not even talking about anything, right? Then we're in la la land. So we really need to have this ambition to develop theories that somehow make contact with reality and make measurable differences. Second point is that it's not a problem to take a non-reductionist approach to this. Non-reduction means that uh, the way in which the participation criterion is satisfied will be in terms of things that can't be explained at the reduced level. But that's not a problem in per se. It doesn't mean dualism. It doesn't mean that we have to have a weird metaphysics. It means that we have to work and quantify the uncertainty that results from those aspects which can be reduced to the lower levels. And that's fine. I think science is a very good shape of dealing with non-observables in terms of indirect consequences that can be reduced to other observables. So, that's just standard practice in much of the rest of the natural sciences. And with that, thank you for your attention.